This video is brought to you by Magellan TV. Stars with masses greater than 8 times our Sun are rare. They make up less than 1/10 of 1% of all the stars in the universe, but these stellar giants have an enormous effect on the formation of stars around them and create the elements needed to build rocky planets and even life. But in order to do so, these stars must die. And when they do, they don't go gently into that good night. Instead, they go out with a bang. Massive stars live their lives doing what all stars do. They burn hydrogen into helium in their cores and they produce energy along the way. It's this energy that holds the star up against its own collapse. Massive stars start off with a lot more hydrogen fuel than in our Sun. But that extra mass means extra gravity, so their cores are squeezed far harder. That causes the star to burn its fuel hotter and faster. That means the more massive the star, the more luminous it is. For example, Sirius is only twice the mass of our Sun, yet it is 23 times more luminous. Pi Andromedae is 6.5 times the mass of our Sun, but it is 800 times brighter. And Mu Columbae is 16 times the mass of the Sun, yet it is a whopping 47,500 times brighter. But before long, the core runs out of hydrogen fuel, and all that's left is inert helium. With no internal fusion to prop the core up, it contracts and gets hotter. The hydrogen surrounding the core is squeezed against it until it begins fusing in a shell. The outer layers of the star expand and cool in response, and the star evolves off the main sequence. This is similar to the way the Sun will expand to become a red giant. But because the core of this star is producing so much more energy, the outer layers rapidly expand to nearly the size of Jupiter's orbit. The star has become a red supergiant. Betelgeuse in the constellation Orion is a red supergiant star. It's more than 600 light years away, but it's so large we can resolve its surface in our best telescopes. This isn't Betelgeuse's light spreading out over the image. It's the actual surface of the star, and it's blobby. Its interior is unstable, and its outer atmosphere is so distended that changes inside take a long time to ripple around the star's surface. These undulations produce powerful stellar winds that cause Betelgeuse to lose a sun's worth of mass every 10,000 years. Interestingly, the star's overall luminosity hasn't really changed all that much. And that's because a star's luminosity is governed by the square of its radius as well as its surface temperature to the 4th power. And this is important because by now the star's surface temperature is much, much lower than it was while it was on the main sequence. But its overwhelming size basically makes up for the loss of surface temperature, so the luminosity doesn't really change all that much. Meanwhile, back in the contracting core, temperatures quickly reach 170 million Kelvin, and that's hot enough to get helium to start fusing into carbon and even some oxygen. In our video on how the Sun will eventually die, we found that such low-mass stars won't be able to ignite their helium cores until it has squeezed itself into such a dense state of matter that its electrons become degenerate. But high-mass stars have cores that are already much hotter to begin with, so they're able to ignite helium fusion while it is still a normal, albeit extremely hot gas. The core expands and cools. With less energy pumping into the rest of the star, it contracts and heats up in response. The star is now a blue supergiant. In fact, Rigel, also in Orion, is a blue supergiant star. Even though it's 860 light-years away, it's easily one of the brightest stars in the entire night sky, putting out 120,000 times the energy of our Sun. Before long, the helium fuel runs out and all that's left is a core of inert carbon. Our Sun will develop a carbon core as well, but this is the point where stars like our Sun start to tap out. And that's because they can't get their cores hot enough to fuse carbon into heavier elements. But the situation is very different in a massive star. The sheer weight of the surrounding layers quickly drive up the core temperatures to 600 million Kelvin, allowing it to begin fusing into oxygen, magnesium, and neon. This cycle of contraction, heating, and nuclear fusion repeats several more times, creating heavier nuclei at each stage. But each heavier nucleus requires higher and higher temperatures in order to fuse. Carbon fuses into neon at 600 million Kelvin. Neon fuses into oxygen at 1.5 billion Kelvin. At 2 billion Kelvin, oxygen fuses into silicon, and at 3.5 billion Kelvin, silicon begins fusing into iron. The star oscillates between the blue and red supergiant stages as it runs out of one fuel and ignites another. Eventually, the core looks like a giant onion with inert iron at its very center, surrounded by a silicon burning shell, which in turn is surrounded by an oxygen burning shell, then neon, carbon, helium, and hydrogen fusing shells. Not only does each stage have to burn its nuclear fuel hotter, it must also burn it faster than the one before it. And that's because as the produced nuclei get heavier, the amount of energy released in each reaction gets lower. That means that these successive stages have to burn their fuel much faster than the one before it in order to produce enough energy to hold the star up. For example, a 25 solar mass star will exhaust its entire supply of hydrogen in about 7 million years. Helium is burned through in about 700,000 years. Carbon burning only lasts about 160 years. Neon is burned through in about 1 year. Oxygen is burnt in about 6 months, and its entire supply of silicon will be fused into iron in, believe it or not, 1 day. When the core becomes iron, the star is doomed. Remember, every element created so far produced less energy than the one before it. By the time it reaches iron, it stops producing energy altogether. On this last day of the star's life, the star cannot get hot enough to fuse iron because iron cannot be fused. At first, the core contracts by a small amount and the electrons quickly become degenerate. The core has become essentially an iron white dwarf. But the surrounding shells keep dumping heavy elements onto the core until it reaches 1.4 solar masses. And that's bad. The density inside the white dwarf is a mind-crushing 400 billion times greater than water. It is so dense that gamma photons disintegrate the iron nuclei and transforms them into a soup of free protons and electrons. With no more energy to hold itself up, the core implodes. In less than 1/10 of 1 second, the core collapses from the size of Mars to the size of Manhattan. During the collapse, the protons and electrons are squeezed together to form neutrons and neutrinos. The neutrinos escape the core, carrying energy away with them, and the collapse accelerates. The neutrons are squeezed together so tightly they exert an ultra-powerful neutron degeneracy pressure, and the collapsing core comes to a ringing halt at a radius of just a few kilometers. Unfortunately, the rest of the star doesn't know that. The surrounding layers just had their legs kicked out from underneath them. And within a few milliseconds, 250,000 Earths worth of star stuff comes crashing down on the core at 15% the speed of light. A powerful shockwave rebounds off the core. The star has released more gravitational energy in just 1 second than all of the nuclear energy it released in its entire life. But that energy has to go somewhere. Most of it is carried away in the form of neutrinos. 10 to the 58 neutrinos. Neutrinos are so tiny that 99.7% of them pass right through the star at the speed of light. But the remaining 0.3% of neutrinos collide with the dense matter in the shockwave. That may not seem like a lot, but 0.3% of 10 to the 58 neutrinos is still 3 times 10 to the 55 neutrinos. That is a colossal amount of matter all colliding in the shockwave. The shockwave gets supercharged and rips through the star at 10% the speed of light, exploding the star in a supernova. The star brightens to 100 billion times the sun. That's nearly as bright as all of the other stars in the galaxy combined. About 1/10 of a solar mass worth of neutrons is ripped off the core's surface. These neutrons collide with heavier nuclei blasting out of the star. These nuclei then decay and form heavier elements, including elements greater than iron. In fact, all the elements heavier than iron, including zinc, copper, silver, gold, even uranium, are created in this neutron fusion in the maelstrom of the supernova. Radioactive elements formed in the explosion decay over time, releasing more energy in the process. This keeps the supernova bright for several months at a time. The exploding gases expand away, leaving behind the exposed core. The core is now a rapidly spinning ball of degenerate neutrons called a neutron star. These objects are at least 1.3 times the mass of the Sun, but are only between 10 and 12 kilometers across. That makes these things mind-bogglingly dense, up to 100 billion trillion grams per cubic centimeter. Not only that, but they rotate at least 10 times per second when they form. This generates ultra-powerful magnetic fields that are at least 1 trillion times stronger than Earth's. These ultra-powerful magnetic fields act as particle accelerators, generating powerful beams of radiation along the magnetic poles. As these beams sweep across our line of sight, we detect them as repeating radio pulses, so we call these magnetized rotating neutron stars pulsars. Rotating or not, the neutron star surface is extremely hot at around 1 million Kelvin. That's hot enough to ionize the surrounding gases for about 25,000 years. The most well-known supernova remnant is the Crab Nebula in the constellation Taurus. It formed in 1054 AD in a supernova explosion that was so bright it could be seen during the day. At the center is the Crab Pulsar, rotating at 30 times a second. Its magnetic field churns up the surrounding gas like a stellar egg beater. Stars between 8 and 40 solar masses will ultimately produce neutron stars in supernova explosions. But if the star begins life with more than 40 solar masses, it'll produce an explosion with at least 10 times the kinetic energy of a typical supernova. These explosions are so energetic we sometimes call them a hypernova. The cores of these ultramassive stars reach at least 3 solar masses. That's too massive for even neutron degeneracy pressure to prevent its complete and total collapse into oblivion. The core collapses until it reaches a mathematical volume of 0, crushing all matter out of existence. The core is now a black hole. As the black hole forms inside the collapsing star, matter rapidly funnels into it. This sets up powerful jets along the black hole's spin axis, and we see these jets bursting through in powerful gamma-ray bursts. These explosions are the most luminous and violent in the entire universe. They are literally the biggest bangs since the Big One. Whether it is a gamma-ray burst, a hypernova, or even a mere supernova, there is a tremendous amount of material blasting into the interstellar medium. This gas is loaded with heavy elements, and when it slams into a nearby interstellar cloud, it shocks the cloud into collapse. Suddenly, hundreds of stars are able to form in a single blow. Over the next tens of millions of years, that dead star stuff rearranges itself to become new stars and rocky planets that surround them. And on at least one of those rocky planets, some of that dead star stuff rearranged itself again to become life. The iron in our blood, the calcium in our bones, virtually everything that makes up you and me was created in a supernova explosion. We owe our existence to supernovae. But that doesn't mean we want to be anywhere near one of these things when they go off. A supernova 50 light years away would sterilize all life here on Earth. Even one 100 light years away would dramatically raise global temperature and radiation levels. In fact, a supernova that went off 150 light years away is probably responsible for a mass extinction that occurred 2.6 million years ago. Luckily, these massive stars are rare. In fact, the closest star that could possibly go supernova is Spica in the constellation Virgo. It's 250 light years away, and it hasn't even begun to evolve yet. So we're safe. For now, at least.